Welcome back to the deep dive. If you're looking to, cut through the noise and get right to the core of complex topics, you've definitely landed in the right spot.
Always good to be diving deep.
Yeah, absolutely. So today we're doing a deep dive into something that's, well, fundamentally changing our world,
Yeah.
and something you've given us some great source material on to explore: the Internet of Things.
IoT everywhere these days.
Exactly. But our focus isn't just what IoT is, it's the really challenging part, taking those initial ideas, those pilots, and scaling them, growing them sustainably. We're talking potentially millions of connected devices.
Yeah, that's really where the rubber meets the road in the world of IoT, isn't it? I mean, almost anyone can connect maybe a handful of devices and get some data flowing. That part's getting easier.
Right.
But transforming that into a robust, reliable, profitable system, one that operates globally, handles maybe petabytes of data, and crucially remains secure against an ever-evolving threat landscape. That takes a fundamentally different approach.
And your source material seems like an excellent roadmap for navigating exactly that challenge.
It provides some really good frameworks, yeah.
Absolutely. And what's powerful about the sources you shared is that they don't just give one perspective, do they? They look at scaling IoT through, well, both lenses. The technical realities, what developers actually need to build and manage day to day.
The nuts and bolts.
And the strategic necessities, how technical managers have to plan and budget and really lead teams through this massive growth.
Two sides of the same coin, really. You can't scale without both firing on all cylinders.
So our mission in this deep dive, then, is to pull out the most critical insights, the actionable strategies from this material. What are the absolute must-knows and must-dos? Whether you're, down in the weeds designing the system architecture or making those bigger executive decisions about deployment and resources.
That's the goal. Practical takeaways.
Exactly. We're going to explore why designing for scalability isn't just like a nice to have, but essential. How to manage the truly sometimes overwhelming volume of data these systems generate.
The data deluge, yeah.
The escalating importance of security as you grow, that seems huge. How intelligence from AI and machine learning isn't just an add-on anymore, maybe, but a scaling tool itself.
Yeah, increasingly fundamental.
The crucial financial considerations, the things that make or break these large-scale projects, and even the human and cultural elements needed to actually make it all work.
That last one's often overlooked, but vital.
It's going to be a comprehensive look, guided by your material, at what it really takes to move from that proof of concept stage to sustained large-scale impact with IoT.
Sounds good. So let's get into it and see what these sources reveal about making IoT growth not just possible, but truly sustainable.
Right. Before you can even think about expanding something dramatically, scaling it up, you have to understand what the building blocks are, don't you?
Yeah.
How they fit together.
Foundational knowledge.
And your source material starts right there, laying out the fundamental components of the IoT ecosystem. It's definitely more complex than just smart devices.
Oh, much more. It really is. The source breaks down the IoT landscape into its core elements, and it emphasizes that scaling means mastering the interplay between these parts. You can't just focus on one.
Okay, so what are these core parts?
Well, first you have the physical devices at the edge. These are your sensors, actuators, embedded systems, industrial controllers, maybe even consumer gadgets that are interfaced with the physical world, right? Collecting data or performing actions.
And I think the source highlights that the sheer diversity of these devices is one of the first big scaling challenges, isn't it? You're not just dealing with one type of gadget.
Precisely. That's a huge point. As you scale, you inevitably integrate more types of devices, often from different manufacturers. They might be running on various operating systems or, often proprietary firmware.
Okay.
And they have vastly different processing power, memory, battery constraints, connectivity options. I mean, the list goes on.
So managing all that difference.
Yeah, think about managing firmware updates or ensuring security patches actually reach every device, handling potential failures or random reboots across maybe a million different endpoints. That complexity, it just grows exponentially compared to, say, managing a fleet of identical servers in a data center.
Right. Much harder out in the wild. Okay,
Yeah.
so devices.
Yeah.
What's next?
Then you have the networks. This is how all that data gets from the device to, well, somewhere useful.
Hmm.
And we're talking everything from local short-range tech, like, Bluetooth or Wi-Fi, maybe Zigbee,
Uh-huh.
all the way up to wide area cellular 4G, 5G, or things like LoRaWAN, NB-IoT, even satellite for really remote stuff, or specialized industrial networks.
A whole patchwork of connectivity.
Exactly. And managing connectivity at scale isn't just about picking one technology, it's about orchestrating a potentially really complex mix. A single large-scale solution might use, say, low-power wide-area networks, LPWAN, for those battery-constrained sensors out in the field.
Right, saving power.
Then maybe cellular for mobile assets like trucks or equipment, and high-bandwidth Ethernet or Wi-Fi maybe inside a factory setting.
So ensuring that all works reliably.
Yeah, ensuring reliable, cost-effective, and secure data flow across this heterogeneous network landscape,
Mhm.
handling varying latency, different bandwidth limitations, potential packet loss. That's a significant technical and operational hurdle when you're trying to scale.
Okay, devices, networks, and a third piece.
And finally, the cloud platforms. This is often where everything converges, the data storage, the heavy-duty processing, the analytics, and often the centralized device management infrastructure itself. The brain, if you like.
And the cloud is key for scaling because...
Well, the cloud is fundamental for scale because it offers those elastic resources you absolutely need to handle the data volume and the processing demands that just dwarf what you could typically do with on-premises capabilities.
Right, you can grow as needed.
Exactly. We're talking scalable databases, massive compute power for analytics and machine learning, flexible storage solutions that can grow or shrink with your needs. It's the essential backend that aggregates data, analyzes it, and provides the insights from that whole distributed edge network.
The source really seems to zero in on the interplay between these three devices,
Hmm.
networks, cloud. Why is understanding that relationship, that kind of ecosystem dependency, so absolutely critical before you even attempt scaling?
That's a great question. And well, a fascinating thing here, I think, is that the performance and the limitations of one layer directly impact the others. They're tightly coupled, even if they seem separate.
How so? Give me an example.
Okay, so if your devices are transmitting data too frequently for the network bandwidth that's actually available in their location, maybe it's a weak cellular signal.
Yeah.
You create network bottlenecks. Data gets delayed and maybe lost.
That makes sense.
Or if the network itself is slow or unreliable, data arrives late or incomplete in the cloud. That impacts the accuracy of your real-time analytics, maybe your control systems.
All right, garbage in, garbage out, delayed.
Or if your cloud infrastructure isn't provisioned correctly to handle the sheer velocity of the data coming in, you get backlogs, processing delays, maybe drop data. So scaling effectively means optimizing across all layers simultaneously. You have to understand how decisions about one component ripple through the entire system.
So you can't just optimize the cloud if the network can't keep up.
Precisely. You can have the smartest edge device in the world, but if it can't reliably get its data through the network to a capable cloud backend, your scaled solution basically fails.
And within that interplay, the source specifically calls out interoperability among devices as like non-negotiable for sustainable scaling. Why is getting different devices to talk the same language, or at least talk to a common gateway, so fundamental?
Yeah, think about integrating devices from different vendors, which is almost inevitable as you scale. They often use different data formats, different communication protocols. You've got MQTT, CoAP, HTTP, plus tons of proprietary ones.
A real mess.
Different semantic representations of the data. What does temperature mean from device A versus device B? Are the units the same? Is the format the same? If every new device type requires a custom integration layer just to translate its data and commands into a format your backend understands, well, your integration costs and complexity will just explode as you add more devices and types. It becomes unmanageable.
So interoperability is about avoiding that integration nightmare.
Essentially, yes. It's about either adopting industry standards where possible or using middleware like gateways that can handle protocol translation, or maybe enforcing really strict data format standards internally. It's essential to avoid building this tangled, unmanageable mess that actively works against scaling. The source definitely implies that without a clear strategy for interoperability, scaling just increases the surface area of your integration headaches.
Okay. And that leveraging of cloud capabilities, you mentioned storage and processing power, but the source digs deeper, right? What specific capabilities are fundamental for scalability in this IoT context?
Yeah, beyond just raw compute and storage, the source points to cloud services specifically designed for IoT at scale. This includes things like managed IoT platforms, think AWS IoT Core, Azure IoT Hub, Google Cloud IoT. These handle device connectivity, authentication, and management for potentially millions of devices.
So purpose-built tools.
Right. And things like serverless functions that let you process data streams without managing servers directly. Scalable databases optimized for time series IoT data, which is a very specific data pattern. And of course, machine learning services that can run complex analytics on these massive data sets.
So it's about using the right cloud tools, not just any cloud tool.
Exactly. These are the tools that provide the elasticity and the specialized capabilities needed to handle the unique demands of high-volume, high-velocity IoT data and managing this huge distributed fleet of devices. It's building on infrastructure designed from the ground up for massive scale and flexibility.
So, okay, it's not just understanding the pieces, it's understanding the entire interconnected system, prioritizing compatibility, interoperability, and leveraging the right tools designed specifically for scale. That's really the foundation we're talking about.
Exactly. You wouldn't build a skyscraper on a shaky foundation, right? And you absolutely can't scale IoT sustainably without a solid grasp of those ecosystem dynamics and ensuring the components can actually work together effectively and, importantly, efficiently.
Okay, so building on that foundation, understanding the ecosystem, the source then shifts to something really crucial. You can't just develop a solution for, say, 100 devices and then just hope to make it work for 1 million later.
No, that rarely works.
Sustainable growth, according to the sources, demands that you design for scalability right from day one, from the very beginning.
This is such a critical principle. It really separates the successful large-scale deployments from those that just hit an early ceiling and, well, fail to grow effectively. Designing for scalability isn't just about anticipating more users or devices. It's about architecting the system from the ground up so that it can handle orders of magnitude increases in load, data, and complexity without requiring fundamental, really costly re-architecture down the line.
Okay, but what does that principle actually mean in practice? For the developers, the architects building this stuff.
Well, the source really emphasizes modular architecture. Instead of building a single, large, tightly coupled piece of software, what we often call a monolith.
Right, the big ball of mud.
Yeah, exactly. Instead of that, you design the system as a collection of smaller, independent services or modules, microservices perhaps. Each service has a specific, well-defined function. Maybe one service handles incoming device connections and authentication, another is responsible just for data normalization, another runs specific analytics tasks, and yet another manages user authentication or API access.
Okay, I've heard a lot about microservices. How does breaking it down like that specifically help with scaling in an IoT context? What's the benefit?
The key benefit the source highlights is independent scalability and resilience. So let's say as you add millions of devices, the service that ingests raw data becomes a bottleneck. It can't keep up. With a modular architecture, you don't have to scale your entire application, which might be huge and expensive. You can just scale that specific ingestion service horizontally by adding more instances of just that one service.
Okay, targeted scaling.
Exactly.
Love.
And similarly, if one service fails, maybe the analytics service has a bug, it's much less likely to burn down the entire system. Other parts, like data ingestion, can keep running. This improves overall reliability, which is crucial at scale.
And it helps development teams too.
Yeah, it allows different teams to develop and deploy different parts of the system independently. Team A works on the device connection service, Team B on analytics. They can deploy updates faster, speeding up development velocity even as the overall system gets larger and more complex. It helps prevent that monolithic big ball of mud scenario that eventually becomes impossible to manage and scale efficiently.
The source also ties this design thinking to DevOps practices. How does adopting things like continuous integration and continuous delivery CI/CD become critical when you're managing not just a back-end service, but potentially millions of physical devices out in the world?
Right. DevOps, at its core, is about automating and streamlining the process of getting code changes, new features, bug fixes, crucial security patches from a developer's machine into production reliably and quickly.
Okay.
In IoT, this is massively challenging because your production environment isn't just a few servers in a rack somewhere. It's potentially millions of geographically dispersed devices. They're running on varied hardware, often with intermittent or slow connectivity.
Yeah, that sounds like a nightmare to manage manually.
Exactly. The source emphasizes that.
And finally, in this design section, the source strongly recommends designing APIs for future expansion. Why should you be thinking about application programming interfaces, the way different software components talk to each other right at the beginning? Seems like something you could add later.
But APIs are the defined interfaces, the contracts, that allow different parts of your system, or maybe external systems, to interact. Designing clean, stable, and well-documented APIs from the outset is really about building in flexibility and enabling external connections without disrupting your core functionality later on.
Why is that so important for scaling?
Because the source stresses that a scaled IoT solution rarely exists in a vacuum. You'll inevitably want to integrate it with other enterprise systems, maybe your ERP or CRM. You might want to expose data to third-party analytics platforms or allow partners to build new applications on top of your data or add entirely new functionalities yourself down the line.
Okay. And if you don't have well-designed APIs,
Yeah.
what happens?
Then every single integration becomes a custom, brittle, point-to-point connection. It's hard to manage, probably insecure, and impossible to scale effectively. You end up with spaghetti code connecting everything. By designing a solid API layer early, you create a stable interface. This allows you to maybe swap out backend components later, add new services, or integrate with new external partners, all without having to rewrite the code that consumes or provides data through that API.
So it makes your system more open, more flexible.
Exactly. It's about making your system potentially an open platform for future growth and integration rather than just a closed, rigid box that's hard to change.
So it sounds like designing for scale isn't just about anticipating the volume, like number of devices. It's really about building in the flexibility, the modularity, the automation, and the adaptability to handle future changes and integrations elegantly. It's definitely an upfront investment that pays dividends down the line.
Yeah.
Right?
It absolutely is. And, this raises an important question. Are development teams truly given the time and the resources to prioritize this crucial upfront architectural work? Because if you rush the initial design to get something out the door quickly,
It happens a lot.
which happens a lot,
Yeah.
you're essentially building technical debt. And that debt will actively work against your scaling efforts later. It often forces expensive, disruptive, and risky replatforming projects just to keep growing. The source clearly advocates for prioritizing this foundational design work. It's critical.
Okay, so let's shift gears. We've talked about the ecosystem and designing for scale. Now let's tackle the sheer consequence of having millions of devices connected. The data deluge. Your source material highlights that managing the massive volume of data efficiently is absolutely crucial for scale, and, well, it presents a significant challenge.
Oh, yeah. This is where the rubber really meets the road operationally, I think. More devices don't just mean more connections. They mean an exponential increase in the data being generated, transmitted, stored, and processed.
Exponential is the key word there.
It really is. The classic 3 Vs of big data: volume, velocity, and variety, they're just magnified dramatically in IoT. You have the sheer volume of data points from potentially millions or billions of sensors reporting frequently, maybe every second, maybe even faster.
Okay.
You have the high velocity of that data, often streaming in real time or near real time, needing immediate attention or processing. And you have the incredible variety of data types, everything from simple numerical sensor readings like temperature or pressure to complex video streams, audio data, location data, and structured operational data. Just wrangling all of that is a monumental task at scale.
And the source introduces a fundamental strategic decision related to this data tsunami: edge computing versus cloud processing. Can you break down that distinction? Why is making the right choice, or maybe the right combination of choices, so vital for scaling efficiently?
Yeah, the source frames this as a really key architectural consideration. So edge computing basically means processing data closer to where it's generated, either directly on the device itself, if it has enough power, or more commonly on a local gateway device nearby.
Okay, processing near the source. Why do that?
This is crucial for scaling in scenarios where latency, bandwidth, or immediate action is critical. Think about, say, industrial automation or autonomous systems like self-driving cars. Processing sensor data right at the edge allows for the millisecond level response times needed for control loops or safety systems. You simply can't afford the delay of sending data all the way to the cloud and waiting for a response to, say, stop a robot arm.
Right, too slow for critical actions.
Exactly. Edge processing also dramatically reduces the amount of raw data that needs to be transmitted back to the cloud. This saves significant bandwidth costs, which can be huge, especially for high-volume data like video or high-frequency sensor readings.
How does that work?
Well, you might process raw video at the edge to detect a specific anomaly, like a person entering a restricted area. And then you only send a small alert message and maybe a few relevant image frames back to the cloud, rather than streaming the entire raw video feed 247 from thousands of cameras. That's a massive bandwidth saving.
Gotcha. So it helps reduce the load further up the chain, saves money.
Exactly. It shifts compute power closer to the action where it makes sense. Cloud processing, on the other hand, is the centralized approach we talked about earlier. Data is sent from devices, or perhaps after some initial filtering or aggregation at the edge, to the cloud for long-term storage, heavy-duty computation, running complex analytics, training machine learning models, and aggregating data from your entire device fleet to get that big picture view.
Okay.
The cloud offers virtually unlimited compute and storage resources for tasks that don't require that immediate real-time response, or tasks that really benefit from having a global view of all the data from all devices.
So it's not really an either situation, is it? It's more about finding a strategic balance.
That's what the source implies, yes. For most large-scale IoT solutions, it's likely going to be a hybrid model. You intelligently distribute the processing workloads. You do what's necessary at the edge, maybe for real-time response, bandwidth reduction, or perhaps even data privacy reasons, keeping sensitive data local. And then you send the rest, or summaries, or aggregated data, to the cloud for that deeper analysis, historical storage, and global aggregation.
And the right mix depends on the specific use case.
Absolutely. The decision depends heavily on the specific application, the latency requirements, the bandwidth costs and the deployment locations, data privacy needs, maybe even regulatory requirements. Getting this edge cloud architecture right is absolutely fundamental to cost-effective and performance scaling.
Okay, so once the data reaches its destination, whether that's the edge or the cloud, you have to store it somehow. The source talks about best practices for data storage and retrieval becoming critical at scale. What kind of considerations arise when you're suddenly dealing with potentially petabytes of time series data?
Yeah, at scale, the traditional relational databases that most people are familiar with, the ones designed for structured transaction data like customer orders, they often aren't suitable. They can fall over.
Why not?
Because IoT data is primarily time series data, it's measurements tied to a specific point in time, and it arrives at a relentless pace. The source highlights the importance of using databases specifically optimized for this pattern. Things like dedicated time series databases, InfluxDB, TimescaleDB are examples, or maybe certain NoSQL databases that are designed to handle very high ingest rates and large volumes of less structured data.
So choosing the right tool for the job, database-wise?
Exactly. And efficient indexing is paramount. You need to be able to query these vast data sets quickly based on time ranges or device IDs or maybe location without having to scan terabytes or petabytes of data every time. That requires careful index design.
And managing the sheer volume.
Right. Data lakes are often used as a sort of landing zone for dumping raw data before it's processed, cleaned, and maybe moved to more structured storage, and cost becomes a massive factor. Storing everything indefinitely is usually prohibitively expensive, so implementing data lifecycle management strategies, things like automatically tiering older data to cheaper, slower storage, or archiving it, or even deleting data that's no longer needed after a certain period, that becomes essential for cost control.
Makes sense. And all this data collection, storage, processing, it ultimately for a purpose, right? The source talks about using analytics tools to drive business decisions. How is turning this raw IoT data into meaningful, actionable insights crucial for justifying and guiding the scaling efforts themselves?
Because the raw data itself, as you said, it's just noise without analysis. At scale, the insights you derive from that data are the primary value driver. That's why you built the system. So you need sophisticated analytics platforms and visualization tools, dashboards, reporting tools to process the sheer volume and velocity of the data and turn it into something human readable. Things like real-time operational status dashboards, performance metrics, historical trends, alerts for anomalies.
And these insights guide decisions.
Absolutely. The source emphasizes that these insights guide strategic decisions. Where is the system performing well? Where are the bottlenecks? Which types of devices are failing most often, needing replacement? Which geographic locations offer the best return on investment for further deployment? Data-driven insights validate the value of the scaled deployment, justify the ongoing costs, and crucially, point the way for future investments and optimizations.
So handling the data isn't just a technical chore in the background. It's about building an engine of information that proves the value of scaling and directs where you should grow next. It closes the loop.
Exactly. And what's fascinating here is how those strategic decisions about where and how you process and store data edge versus cloud, which database lifecycle policies, they fundamentally impact your ability to scale effectively and cost efficiently. And importantly, without turning that data into actionable insights, you lose the primary benefit, the whole reason for connecting all those things in the first place.
Okay, moving from the data itself to protecting it and protecting the system it flows through. The source material makes it starkly clear. As IoT solutions scale, security doesn't just get a little harder. Its complexity escalates, maybe disproportionately.
Oh, definitely.
More connected things invariably mean more potential entry points for threats, right?
Well, think about what you're dealing with. You have devices that might have very limited processing power or memory, making it difficult or even impossible to run strong encryption algorithms or complex authentication protocols.
Resource-constrained devices.
Exactly. They might be running diverse, sometimes outdated operating systems and firmware, maybe stuff that hasn't been patched in years because it's hard to update. They are often deployed out in the physical world in insecure or physically accessible environments where someone could literally tamper with them.
Yeah, unlike a locked data center.
Right. And the network conditions vary wildly, making secure communication harder. So unlike securing a traditional corporate network with strong firewalls and centralized control, a scaled IoT deployment is inherently decentralized, incredibly diverse, and physically exposed. An attacker only needs to find one weak point among potentially millions of devices to gain a foothold, maybe steal data, or even launch attacks on other systems. The sheer variety and distribution make it incredibly difficult to enforce consistent security policies and effectively monitor for threats across the entire sprawling system.
Wow, okay. So the source discusses the critical need for security frameworks for IoT. What exactly are these and why are they so necessary at scale? You can't just wing it.
No, you definitely can't wing it at scale. Security frameworks, like some well-known ones from NIST or OWASP for web-related aspects or maybe industry-specific bodies, they provide a structured, methodical approach to security. They cover the entire IoT product lifecycle from the initial design and manufacturing through secure deployment, operation, ongoing maintenance, and even eventual decommissioning of devices.
A whole life cycle view.
Yes. The source suggests that at scale, you absolutely cannot rely on ad hoc security measures applied inconsistently. A framework provides guidelines for systematically identifying risks, implementing appropriate controls, and managing security consistently across your entire ecosystem, covering device security, network security, cloud security, data security, application security, everything. They help ensure that security is built in by design, not just bolted on as an afterthought when it's often too late or too difficult.
And a fundamental piece of that building it in must be encryption and secure communication, right? Where does encryption actually play a role in the IoT data flow, and why are secure communication protocols non-negotiable?
Encryption is needed pretty much everywhere sensitive data could potentially be exposed. So data should be encrypted at rest, both on the device itself if it stores data locally, and definitely in the cloud database or data lake.
Okay, stored data.
And crucially, data must be encrypted in transit as it travels across networks. That means from the device to the gateway, from the gateway to the cloud platform, and even between different microservices within the cloud backend.
All the communication links.
Yes. Secure communication protocols like TLS, SSL, the same stuff that secures your web browsing, or maybe DTLS, which is designed for UDP-based communication, often used in IoT. These ensure that the data packets traveling across potentially untrusted networks are protected from eavesdropping, tampering, or man-in-the-middle attacks. Without encryption, any data intercepted on the network is basically readable plain text.
And doing that reliably at scale.
That's the challenge, ensuring every single connection is properly authenticated, making sure the device is who it says it is and the server is who it says it is, and reliably encrypted across all these diverse network types and millions of endpoints is a significant operational challenge. It absolutely must be automated and continuously monitored. You can't manage millions of security keys manually.
Right. Beyond preventing breaches, though, the source also covers incident response and compliance considerations. Why is having a plan for when things inevitably go wrong so essential? And how does scaling impact those compliance requirements?
Because no matter how robust your security measures are, you absolutely must assume that security incidents will occur at scale. It's almost statistically inevitable with millions of endpoints. Having a well-defined, documented, and importantly tested incident response plan is critical.
What does that plan do?
It allows you to rapidly detect a security event, contain the damage quickly to prevent it from spreading across your vast deployment, investigate the root cause effectively, eradicate the threat, and recover operations safely. A slow or ineffective response to an incident affecting millions of devices or compromising a large volume of sensitive data can have absolutely catastrophic financial, operational, and reputational consequences. Think major data breach headlines.
Yeah, nobody wants that. And compliance.
The source underscores that scaling also dramatically increases the complexity of compliance. As your IoT solution expands, maybe into new geographic regions or new industries, you inevitably have to navigate a complex web of different data privacy laws like GDPR in Europe, CCPA in California, and others emerging globally.
Different rules everywhere.
Exactly. Plus, industry-specific regulations may be HIPAA for healthcare data, or regulations for energy infrastructure or financial services, and various cybersecurity mandates. A scaled solution must be designed and operated to adhere to this constantly evolving patchwork of global and regional compliance requirements. This often involves things like data localization rules, where data must physically reside, maintaining detailed audit trails, and potentially obtaining specific security certifications.
The security isn't just technical, it's legal and regulatory too, especially at scale.
Absolutely. And, this raises an important question. Is security truly embedded in the engineering culture? Is it budgeted for appropriately as a critical investment, something that enables trust and long-term growth? Or is it still sometimes treated as, a necessary evil, a cost center to be minimized? Because the sources make it crystal clear. Without treating security as a continuous, escalating priority, scaling an IoT solution exposes the organization to, frankly, unacceptable levels of risk. Trust is paramount, especially when you're connecting critical systems or handling sensitive personal data.
Okay, so let's think about how to leverage all this data we're collecting and manage the complexity we've been discussing. The source material highlights the really significant role of artificial intelligence and machine learning, AI and ML. It's suggesting it's not just about connecting things anymore, but making them smart, and that intelligence is actually a key tool for scaling.
Absolutely. AI and ML are increasingly seen as ways to lift IoT solutions from just simple data collection and basic monitoring to enabling predictive capabilities, intelligent automation, and system optimization. They allow organizations to extract far deeper and more complex insights from the massive data streams generated by scaled deployments than traditional rules-based systems or manual analysis could ever hope to achieve.
And the source provides a really concrete example. It mentions predictive maintenance in IoT systems. How does using ML models to predict when equipment might fail actually contribute to efficient scaling?
Okay, think about maintaining a huge fleet of assets, maybe industrial machines and factories, or delivery vehicles, or remote infrastructure like cell towers or pipelines. Thousands, maybe millions of them. Okay.
Traditionally, maintenance is often done on a fixed schedule, like servicing a machine every 1,000 hours, whether it needs it or not. That's inefficient. Or it's reactive, you wait for something to break, which is really costly due to unplanned downtime and emergency repairs.
Right, the run-to-failure model.
Exactly. With predictive maintenance, sensors on the equipment continuously collect data on various parameters, maybe vibration, temperature, acoustic signals, power consumption, error codes, things like that. Machine learning models are then trained on historical data, including data from past failures. They learn the subtle patterns and correlations in the sensor readings that typically indicate an impending failure, often weeks or even months in advance.
So the system can essentially tell you that a specific part on a specific machine is going to fail before it actually does.
That's the goal, yes.
Yeah.
And at scale, these models can continuously monitor thousands or millions of assets simultaneously. When a model detects patterns indicating a high probability of failure for a specific piece of equipment in the near future, it generates an alert, maybe creates a work order automatically. What's the scaling benefit?
This allows maintenance teams to schedule a targeted repair or replacement before the failure occurs, during planned downtime. This minimizes that costly unplanned downtime, helps optimize maintenance schedules and resource allocation, like technician time and spare parts inventory, and significantly reduces the cost of emergency interventions. The source points out that for large-scale deployments, the efficiency gains and cost savings from reduced downtime and optimized resource allocation can be absolutely substantial. It directly improves the bottom line and helps justify the ongoing investment in scaling the IoT solution.
That makes a lot of sense. And this brings us back to the data itself. How does leveraging ML for data-driven insights more generally help extract deeper, more complex patterns from scaled IoT data compared to traditional analytics?
Well, traditional analytics might tell you simple things, like the average temperature across all your devices, or maybe flag a single reading that goes outside a predefined static threshold. Useful but limited. ML, on the other hand, can uncover non-obvious multivariable relationships in the data. For instance, an ML model might discover that a specific combination of slightly elevated temperature, rising humidity, and a particular vibration frequency pattern occurring only on, say, Tuesday afternoons predicts failure for a certain model of sensor with 90% accuracy within the next week.
Wow, that specific.
Right. These are the kinds of subtle, complex insights that are virtually impossible for a human analyst or simple rules to find manually in petabytes of time series data. ML is also really key for advanced anomaly detection, identifying unusual device behavior that could indicate a security breach, a configuration error, or maybe an emerging operational issue across millions of devices simultaneously. It can do this far more effectively than just setting simple static thresholds for every possible parameter. It turns that raw data into truly actionable intelligence for optimization and problem solving at scale.
Okay, that's powerful. The source also touches upon ethical considerations in AI applications within IoT. When ML models start making decisions or predictions that impact operations or assets at scale, what kinds of ethical points does the source suggest need careful consideration?
Yeah, this is becoming increasingly important. The source notes that as AI and ML get more integrated into scaled IoT systems, some key ethical questions arise. For instance, potential biases in the training data need to be addressed. Could the historical data used to train a predictive model inadvertently lead to certain types of devices, or maybe users in certain demographic groups receiving less optimal service or biased outcomes?
That's a big concern with AI generally.
It is. There's also the challenge of transparency or explainability. Can we actually understand why an AI model made a particular prediction or decision? This is crucial for debugging the system, for auditing its performance, and simply for building trust, especially when these systems are used in critical applications like healthcare or infrastructure control.
Hard to trust a black box making big decisions.
Exactly. And the source also points to considering the impact of increasing automation on human roles and responsibilities as these systems become more autonomous. And of course, the ongoing imperative of protecting user privacy when you're collecting and processing vast amounts of potentially sensitive data through these complex AI algorithms. These aren't just technical problems, they're really societal and business challenges that organizations deploying IoT at scale must navigate responsibly.
So it's not just can we build it, but should we build it this way?
Precisely. If we connect this to the bigger picture, AML is clearly not just about adding smart features anymore. It's becoming a fundamental technology for managing the inherent complexity and extracting the maximum operational and business value from vast-scaled IoT deployments. But its implementation requires really careful consideration of data quality, model validation, ongoing monitoring, and these broader ethical implications as these systems become more pervasive and influential in our world.
Okay, let's get into the nuts and bolts of making all this growth financially viable. Your source material shifts focus pretty clearly to the management side here, emphasizing that budgeting is absolutely vital to scaling initiatives. It's not just about whether the tech works, it's about whether the business case actually holds up as you grow bigger and bigger.
Exactly. Technical feasibility and operational success are, of course, necessary, but sustainable scaling requires a really clear understanding of all the costs involved and a solid strategy for ensuring the investment delivers a tangible return. Technical managers need to be fluent not just in the technology itself, but also in the financial realities of growing an IoT solution. They need to speak the language of finance.
And the source discusses the challenge of estimating costs versus returns on IoT investments. Why is calculating ROI, return on investment, particularly tricky in IoT, especially when you're scaling up significantly?
Yeah, calculating ROI for IoT can be notoriously difficult. One reason is that the cost structure is really complex, and it often involves significant operational expenses, OpEx, that grow right alongside the scale, not just those big upfront capital costs, CapEx.
So it's not just buying the devices.
No, not at all. The source points out you have costs for the hardware itself, devices, gateways. But then you have connectivity costs, which can vary wildly based on data volume, the network type you use, and the geographic location of the devices. You have data management costs, storage fees, processing charges, database licenses, analytics platform subscriptions, software licenses for the platform itself. Integration work, which can be substantial, platform fees, and significantly, those ongoing operational expenses like monitoring the system 24/7, maintenance, support, and crucially, the personnel costs for data scientists, security analysts, operations teams, and support staff needed to run a large-scale system.
And these different costs can interact in maybe non-obvious ways as you scale.
Oh, absolutely. For example, making an inefficient data management choice early on, like deciding to send too much raw data to the cloud instead of processing more at the edge, that can dramatically increase your connectivity bills and your cloud storage and processing bills as you add more and more devices. It multiplies.
Right.
Or underinvesting in security design upfront might seem cheaper initially, but it could lead to incredibly costly breaches and recovery efforts later on. And the returns, as we touched on with AI and predictive maintenance, can also be indirect things like cost savings from improved efficiency or maybe new revenue streams from data-driven services. These can be much harder to quantify accurately upfront compared to, say, direct revenue from selling a product.
Yeah.
So estimating all these multifaceted costs accurately as you scale and predicting the often less tangible benefits requires some pretty sophisticated financial modeling.
And the source highlights the need for both long-term versus short-term budgeting strategies. Why do scaling IoT projects require looking at both horizons?
Well, short-term budgeting is obviously essential. It focuses on the immediate needs, funding the next phase of device deployment, covering the initial cloud setup costs, supporting the current operational teams for this quarter or this year. You need that.
Sure, that'll pay the bills now.
But sustainable scaling absolutely requires a clear view of the long haul. The source specifically warns against focusing only on those initial capital expenditures, CapEx, like the cost of buying the devices and neglecting the potentially much larger and continuously escalating operational expenditures.
Up Apex.
Yeah, those recurring costs of connectivity, cloud services, software subscriptions, ongoing maintenance, support contracts, personnel. These often grow proportionally or sometimes even disproportionately with the number of deployed devices over the lifetime of the solution.
So managers need to budget not just for the initial rollout, but for the ongoing cost of running and maintaining a much larger system, potentially for years or even decades.
Precisely. You need a financial strategy that accounts for things like increasing data volume costs as usage grows, the potential need for future infrastructure upgrades as technology evolves, those evolving security monitoring and compliance costs, personnel growth as the system scales, and even the R&D needed to keep the solution competitive and add new features. A long-term financial perspective is absolutely essential to avoid a situation where the ongoing costs of a successfully scaled system become unexpectedly unsustainable later on.
Okay, and within that, the source mentions resource allocation strategies for agile teams. How does a manager think about allocating resources, people, compute power, budget flexibly in a scaling environment that's also likely using agile development methodologies where things change fast?
That's a great point. In an agile approach where requirements and priorities can shift rapidly based on feedback from a scaled deployment or changing market conditions, managers need to be incredibly adaptable with resource allocation. You can't just set a rigid budget and plan a year in advance and stick to it no matter what.
It needs to be more dynamic.
Exactly. It means constantly evaluating where the engineering effort or the budget is needed most right now. Is the highest priority fixing critical security vulnerabilities that were just discovered in the field? Or is it optimizing data pipelines to reduce those escalating cloud costs we just talked about? Or maybe it's developing a new killer feature requested by a major customer that's only possible now because you've reached scale.
So constant reprioritization.
Yes. The source suggests managers need to prioritize ruthlessly, allocate budget and personnel dynamically to address the most pressing technical and operational challenges of the scaled system as they arise, and also ensure that cloud resources can be scaled up or down quickly as usage patterns fluctuate to optimize costs. It's really about aligning finite resources with the constantly evolving needs of a growing, complex, dynamic system.
So budgeting for scaling isn't just a task for the finance department tucked away somewhere. It's really a strategic operational tool that requires constant attention, careful estimation, long-term vision, and flexibility. And it has to be tightly coupled with the technical realities of the system.
Absolutely. And what's fascinating here is just how intricately linked these financial decisions are with all those technical architecture choices we discussed earlier. Decisions about edge versus cloud processing, data storage efficiency strategies, secure investments, they all have direct and really significant impacts on the budget, both CapEx and especially OpEx. Budgeting isn't just accounting, it's a critical strategic enabler or potentially a limiter of sustainable scale.
Okay, so looking beyond your own project for a moment, the source material really emphasizes the value of learning from others. It strongly suggests that examining real-world examples, case studies of successfully scaled IoT solutions provides crucial insights. Why is that so valuable?
Well, it's often the fastest way to learn, isn't it? The sources imply that you can avoid many painful mistakes and potentially accelerate your own scaling journey by studying the experiences, both good and bad, of companies that have already gone through the process. Case studies offer practical, hard-won lessons that theoretical knowledge alone just can't provide. It's really about avoiding reinventing the wheel in areas where others have already struggled and perhaps found effective solutions.
And the source specifically mentions analyzing success stories across different industries. Now, your source didn't provide specific company names, but what can you generally learn by looking at scaled solutions in, say, manufacturing versus healthcare versus agriculture? They seem so different.
They are different on the surface, definitely, but you learn that while the specific devices and the applications differ dramatically, monitoring factory equipment versus tracking patient vital signs remotely versus optimizing crop irrigation, the underlying scaling challenges and the effective strategies often share surprising
Dude,
commonalities.
like what?
Well, you can see how companies in these very different sectors tackled managing vast data sets, or how they implemented security across thousands of distributed endpoints, or how they built robust device management platforms capable of handling updates for diverse hardware, or even how they structured their teams for agile development at scale. It provides a kind of cross-pollination of ideas. It shows which fundamental principles, like modular design or focusing on data quality, tend to hold true, regardless of the specific vertical market. A clever data ingestion pattern that worked really well for smart energy meters might actually be quite applicable to connected cars, for instance. You see patterns emerge.
Okay, that makes sense. And conversely, the source brings up identifying common pitfalls to avoid. Based on the strategies and challenges we've already discussed, what are the typical traps that companies fall into when trying to scale IoT that you'd expect these case studies to illustrate?
Based on the source's overall emphasis, I'd say common pitfalls likely include things like seriously underestimating the complexity and, especially, the cost of data management at scale. This could lead to unmanageable data lakes where you can't find anything, or just crippling cloud bills that kill the project's ROI.
Okay, data costs.
Another huge one is neglecting security in the early design stages, maybe to save time or money. This often results in vulnerabilities that are incredibly difficult, maybe even impossible, and certainly extremely expensive to fix once millions of devices are already deployed out in the field.
Security debt.
Exactly. Failing to design for scalability from the start, leading to that monolithic architecture that eventually buckles under load, that's a classic pitfall we talked about. Underestimating the sheer operational overhead of managing, monitoring, and updating a large, diverse device fleet is another common one. People focus on deployment, not the long tail of operations. And crucially, a lack of alignment or effective collaboration between the technical teams, the business stakeholders who need the value, and the security teams. That disconnect can derail even the most technically promising solution as it attempts to grow and meet real-world demands.
So it sounds like the pitfalls are often the direct result of not following the foundational principles the source has been advocating for all along: design, data, security, collaboration.
Exactly. The case studies of failures often serve as powerful cautionary tales. They vividly illustrate the real-world consequences of taking shortcuts or having a lack of foresight in these critical areas. They make the principles feel much more real.
And on the flip side, the source suggests identifying strategies that led to successful outcomes. When you look at the stories of those who did manage to scale successfully, what common threads tend to appear?
Well, echoing the principles, the source points to organizations that really prioritized building a modular, flexible architecture right from the beginning. They often strategically leveraged cloud-native services and well-designed APIs for that flexibility and scalability.
Okay, good architecture.
They also invested heavily and early in automated data management and analytics pipelines, frequently incorporating AI and ML not just as an experiment, but for core operational insights and efficiency gains.
Data and AI is core.
They treated security not as a checkbox, but as a fundamental, ongoing concern, implementing robust frameworks, continuous monitoring, and having well-rehearsed incident response plans ready. They usually had a clear and flexible financial strategy that realistically accounted for those long-term operational costs, the OpEx.
Financial realism.
And critically, the source suggests they fostered a culture that actively enabled cross-functional collaboration, continuous learning, and rapid adaptation to the inevitable challenges and changes, which actually brings us very neatly to our next key area highlighted in the source.
Yeah, it seems like culture is the thread connecting many of these points. So these real-world examples, whether they're successes or failures, They aren't just interesting anecdotes. They really validate the principles we've been discussing and provide tangible proof of what works and what doesn't in the often messy reality of scaling IoT.
Absolutely. If we connect this to the bigger picture, studying these case studies isn't just optional reading. The source implies it's a critical part of developing a successful scaling strategy for yourself. They offer practical lessons learned, often the hard way by others, and they validate that these sometimes difficult upfront investments in things like robust design, security, and data infrastructure are absolutely essential for achieving sustainable long-term growth.
Okay, shifting focus again, moving away from the purely technical or financial aspects for a moment.
Yeah.
The source material dedicates significant attention to something that might get overlooked in heavily technical discussions, the human element. It stresses that creating an organizational culture that actively supports IoT innovation is crucial for scaling sustainably.
Yes, this point really resonated strongly in the source material provided. It argues, quite compellingly, I think, that you can have the best technology stack in the world and the most robust financial plan backing it. But if your people and, crucially, how they work together aren't aligned for the unique challenges of scaling IoT, you will struggle. Technology is built and managed by people, right? And sustained innovation ultimately comes from the culture.
Why is culture so particularly relevant to technical and managerial success in this specific context of scaling IoT?
Well, scaling IoT involves navigating constant change and dealing with significant uncertainty. You've got new devices emerging all the time, evolving communication standards, unexpected technical challenges popping up, market demands shifting, new security threats appearing daily. The environment is just incredibly dynamic.
Constant flux.
Exactly. A rigid, siloed, or overly risk-averse culture will inevitably be slow to adapt. It will inhibit effective problem-solving across teams, and it can stifle the very innovation that's needed to overcome those scaling hurdles. On the other hand, a culture that genuinely embraces learning, encourages experimentation, and fosters collaboration is much more resilient. It's capable of navigating this complexity far more effectively.
The source specifically mentions promoting continuous learning and experimentation. Why is that so vital in a field like IoT that seems to move incredibly quickly?
Because the pace of innovation in IoT itself, but also in related fields like cloud computing, AI, connectivity technologies, it's just relentless. What was considered cutting edge last year might be standard practice today, and new paradigms, new tools, new threats are constantly emerging. The source highlights that organizations need to actively invest in continuous learning for their teams, providing training on new technologies, new platforms, evolving security best practices, new data analysis techniques.
Keep skills sharp.
Yes. And furthermore, they need to foster a culture where experimentation is not just tolerated, but actively encouraged and supported. Scaling invariably involves tackling unknown challenges where there isn't a pre-written playbook. Experimentation allows teams to safely try out new approaches, maybe test hypotheses on smaller segments of the deployed fleet first, fail fast and learn from it, and then iterate towards more effective solutions before attempting to roll them out across the entire scaled system. It's how you build that crucial institutional knowledge and find optimal solutions in an environment where no single right answer exists beforehand.
Okay, that makes sense. The source also highlights the importance of encouraging cross-disciplinary collaboration. Why is it so crucial for, say, the developers, the technical managers, the data scientists, the security experts, and the business teams to work really closely together when scaling? Why break down those silos?
Because scaling IoT is inherently, fundamentally cross-functional. No single person or team has all the answers or all the context. Developers understand the code and the devices, but they desperately need security experts to help identify and mitigate vulnerabilities in those distributed devices and networks.
Right.
Data scientists can build sophisticated models, but they need the business teams to tell them what insights are actually valuable, what problems need solving to drive business value. Technical managers need to understand both the technical constraints and the business requirements to make effective resource allocation and prioritization decisions.
Everyone needs each other.
Exactly. The source emphasizes that in a siloed organization, critical information gets missed or misinterpreted. This leads directly to things like security gaps, inefficient data pipelines that cost a fortune, features being built that don't actually meet market needs, or budget misallocations where money is spent on the wrong priorities. Breaking down these traditional silos and fostering an environment where these different disciplines collaborate closely and openly right from the initial design phase through ongoing operation is absolutely essential for identifying problems early, developing holistic solutions, and ensuring the scaled system actually delivers value across the entire organization.
And finally, on culture, the source mentions recognizing and celebrating innovations. How does acknowledging successes, even maybe small ones, contribute to a culture that supports growth and further scaling? Seems a bit soft, maybe.
It might seem soft, but it's powerful psychology. Recognizing and celebrating innovations, whether it's a particularly clever technical solution to a tough scaling challenge, or a process improvement that saves significant operational cost, maybe a successful deployment in a really difficult environment, or a new data insight that creates demonstrable business value. It reinforces the desired behaviors.
Shows what's valued.
Precisely. It clearly signals to the teams that their efforts to innovate, to learn, to collaborate, to take calculated risks, that these things are genuinely valued by the organization. This positive reinforcement encourages more of that behavior, more smart risk-taking, more knowledge sharing, and a continued drive to find better, more efficient ways to build, manage, and grow the scaled solution. It helps create a virtuous cycle that fuels further innovation and continuous improvement, which is exactly what you need for sustainable scaling.
So sustainable scaling isn't just about deploying technology and managing budgets. It's fundamentally about building an organization and a culture that is adaptable, collaborative, continuously learning, and motivated to navigate the complex, ever-changing challenges that come with growth in a dynamic field like IoT.
Absolutely. And, this raises an important question for anyone listening. Looking at your own organization or your team, is the current culture likely to be an accelerator for sustainable IoT scaling, or could it potentially be a handbrake? The source strongly implies that the culture is the essential operating system upon which all the technical and financial strategies must run effectively.
That's a really good point to ponder. Okay, as we look to wrap up this deep dive, the source material concludes by reminding us that IoT isn't standing still. Far from it. Sustainable scaling means building solutions and organizations that are ready for what's coming next, actively monitoring and preparing for future trends.
Yeah, the technology landscape, the market needs, the regulatory environment for IoT, everything is constantly evolving. A scaled solution deployed successfully today needs to have the inherent flexibility to adapt to future changes, or it risks becoming obsolete or uncompetitive surprisingly quickly. Staying ahead of these trends isn't just a matter of intellectual curiosity. The source positions it as a strategic imperative for long-term viability.
The source talks about the need to watch emerging IoT technologies. Well, it didn't list specific ones. How should organizations approach this kind of vigilance? What does that look like in practice?
The source emphasizes the practice of monitoring rather than predicting specific winners. This means things like maintaining active R&D efforts, even small ones, fostering relationships with technology vendors and maybe relevant research institutions, following industry analysts and publications, and importantly, encouraging internal teams to explore and evaluate new advancements, maybe through hackathons or pilot projects.
So keeping an ear to the ground.
Exactly. This could include monitoring the evolution of connectivity technologies. We're seeing 5G roll out, but what might future standards like 6G enable? Exploring advancements in edge hardware specifically designed for increasingly powerful local AI processing edge AI is a huge trend. Or investigating new security paradigms, maybe around decentralized identity or confidential computing, that might become relevant for future, more critical deployments. The point isn't to bet the farm on one specific new tech, but to maintain that continuous process of identifying and understanding potentially disruptive technologies before they become mainstream and catch you unprepared.
Okay. And what about the concept of predictions for the future of IoT applications? How might the actual ways we use IoT evolve, and what does that mean for the scaling strategies we've been discussing?
Well, the source prompts consideration of how IoT use cases are likely to become more sophisticated, more integrated, and often more critical. We might see a continued shift towards highly autonomous systems where edge AI makes more complex decisions locally with minimal human intervention required. Think more advanced robotics, smarter infrastructure control.
More autonomy.
Yes. And IoT will likely integrate even more deeply into critical infrastructure utilities, transportation networks, essential public services. This demands even higher levels of security, reliability, resilience, and often ultra-low latency communication than many current applications. The sheer complexity of these potential future applications, their criticality, and their potentially massive scale will necessitate even more advanced scaling architectures, even more robust security by design principles, and even more sophisticated management and orchestration platforms than we typically use today. The scaling strategies we build now must anticipate the increased demands of tomorrow's more critical applications.
And finally, the source emphasizes preparing for shifts in the market landscape. How can organizations build flexibility into their scaling strategies to adapt to things like changing customer demands, new competitive pressures, or unexpected new regulations?
Because the market is dynamic,
Yeah.
new competitors will inevitably emerge, maybe with different business models. Customer expectations for features, performance, and services will definitely change over time, and governments will undoubtedly introduce new regulations related to data privacy, cybersecurity, environmental impact, competition policy, you name it.
Constant change is the only constant.
Pretty much. The source implies that scaled solutions and the organizations behind them must be inherently adaptable. This means things like building platforms based on open standards where possible, making it easier to integrate with new third-party services or swap out components. Designing for flexible business models, maybe enabling a shift from just selling devices to selling data-driven services or outcomes. And architecting systems so they can quickly adapt to new compliance requirements without needing major, costly system overhauls. It really requires foresight in the initial design, a focus on flexible software architectures, and an ongoing organizational commitment to iteration based on market feedback and the evolving regulatory landscape.
So sustainable scaling isn't really a one-time achievement, a finish line you cross. It's more about building a capability both within the system itself and within the organization to continuously adapt and evolve in what is clearly a rapidly changing environment.
I think that's a perfect summary if we connect this to the bigger picture. Viewing sustainable scaling not as a destination, but as an ongoing journey of adaptation fueled by continuous learning, collaboration, and vigilance regarding future trends is perhaps the most important mindset for achieving long-term success in the dynamic world of IoT.
Wow, okay. We have covered a significant amount of ground in this deep dive into scaling IoT solutions, really guided by the source material you shared. It is crystal clear that sustainable growth in the Internet of Things is a hugely multifaceted challenge. It touches on, well, everything: technology, data, security, finance, operations, and definitely organizational culture.
Yeah, we started by understanding that foundational ecosystem, the devices, the networks, and the cloud, and why mastering their interplay, especially around things like interoperability and strategically leveraging cloud capabilities, is just essential groundwork. You have to get that right first.
Then we saw why designing for scalability from the outset, thinking about modular architectures, embedding DevOps practices, creating flexible APIs, is truly non-negotiable if you want to avoid hitting a hard scaling wall later on.
We definitely navigated the complexities of the data deluge, exploring that strategic balance of edge versus cloud processing and the critical importance of efficient data management, choosing the right storage, and actually using analytics effectively to drive real business value at scale. It's not just about collecting data.
Security emerged as a massive and escalating challenge as you scale. It demands robust frameworks, comprehensive technical measures like encryption everywhere, and proactive planning for incident response, and navigating that complex web of compliance.
And we discussed how leveraging data-driven insights through AI and machine learning isn't just about adding fancy features anymore. It's becoming a fundamental tool for managing the inherent complexity and extracting maximum value, while also demanding careful consideration of the ethical implications as we deploy intelligence at scale.
We shifted gears to the business end, highlighting the absolutely critical role of financial planning, accurately estimating those complex costs versus returns, balancing short-term needs with a realistic long-term OpEx perspective, and allocating resources flexibly and dynamically.
We learned the real value of looking at real-world case studies, both the successes and, perhaps more importantly, the failures as practical guides. They help identify those common pitfalls and validate the strategies that genuinely lead to sustainable outcomes.
And finally, we delved into that essential and maybe often underestimated role of fostering an innovative company culture, emphasizing continuous learning, breaking down silos for cross-disciplinary collaboration, and recognizing contributions as the human engine that truly enables adaptation and sustained growth.
Yeah, the source material really makes a compelling case that successfully steering organizations towards sustainable growth in IoT is fundamentally a shared responsibility. It requires developers, architects, data scientists, security pros, and technical managers to all work hand in hand, each understanding and contributing to that broader picture. No single group can do it alone.
Absolutely. understanding and diligently implementing these principles all the way from the lowest level device design choices up to the highest level cultural norms and financial strategy, that seems to be what truly provides a significant, sustainable competitive advantage in this incredibly fast evolving IoT market, just as your source underscores.
It's undoubtedly a complex journey, lots of challenges, but ultimately it seems like a rewarding one towards realizing the immense potential of these connected systems when scaled effectively.
Okay, so as we wrap up this deep dive, here's a provocative thought, maybe something for you, the listener, to consider. Given the incredible speed at which all the components of IoT, the devices, the networks, the cloud platforms, and especially AI are evolving, what's maybe one fundamental technical assumption about scaling IoT that you might currently hold that will likely be challenged or maybe even proven obsolete in the next, say, 3 to 5 years?
And maybe think about how that potential challenge might impact your readiness, your current plans, or your architecture. It's about questioning those assumptions now to prepare for the future. Where might you need to start reconsidering current best practices to ensure your own scaling efforts remain sustainable down the road?
Something to definitely mull over. Thank you so much for bringing this fascinating topic and the source material to our attention for this deep dive. It's been incredibly insightful, lots to think about.
My pleasure. It's a critical topic, and the sources offered a great framework for discussion. Always appreciate the deep dive.
We'll see you on the next dive.